Hi everybody, and we're going to talk about continuous charge distributions and how to calculate their potential. We've already looked at how to calculate the electric field from continuous charge distributions, but now we want to look at the potential. So first things first, remember, if I have a positive charge, okay, and I want to measure the potential at some point P, right? All I need to do is know the amount of charge on my object, and I need to know the distance between them, and I can calculate the potential from this formula, KQ over R, okay? But what happens if I add more charges and I now want to calculate the potential from this distribution of charges? Well, one way to do it is to label this one Q1. We can label that Q2. And we'll label this Q3, and we'll label this R1, we'll label this R2, and we'll label this R3, okay? And then, if I have that, what I can do is just add up the sum. So potential adds, I hesitate to use the word superposition, but it adds linearly, okay? So whatever the potential from my first charge is, plus the potential due to the second charge, plus the potential due to the third charge, you just simply add up all of those individual calculations, and that is your potential. But as I keep adding charges, this formula approaches something that looks like this, right? So this would then just be the sum of all of these individual charges, but as I keep putting charge in a region, it essentially then starts to look like a smooth, continuous distribution of charge. And when you have that, it's not practical to use a summation and calculate each individual potential for each individual charge and then add them all up. That's a lot of computation time, whether you're doing it by hand or trying to put this into a calculator or a computer. So when you have what is essentially a continuous distribution of charge, you don't have to use this summation. You can think of a region in your where your charge is distributed, and you can think of an individual piece of charge as an infinitesimal piece of charge of the total charge contribution. So if you think of the entire charge distribution as having total capital Q, so now instead of each individual charge having their own Q, we're going to say this whole object has total charge, capital Q, and an individual infinitesimal piece of that has charge dq, and we move from a summation to an integral. And it looks like this. Okay? The Coulomb constant times dq over r. And so then I want to integrate over my charge distribution, whatever that charge distribution looks like. So as an example of how to do this, let's think about a uniformly charged ring. So if I have a uniform ring of charge and I want to calculate the potential at some point above the central axis of the ring. Okay, now again, we're going to stay along the axis. When you go off axis, things get very messy very quickly. But if I think of this ring as having positive charge distributed all around the ring, then what I'm going to be dealing with is a one-dimensional case, since this is a line, essentially. So my charge per unit, or my charge density, is going to be a charge per unit length, or a lambda. So I'm going to have a charge per unit length, okay? And first things first, let's also define our coordinate system. So we're going to let the ring lie in the XY plane, and my point P is going to be a distance Z above the origin, okay? So here's what we want to do. Each individual sliver of DQ is going to be a distance, if the ring has a radius A, all right? So we need that piece. Then each DQ is going to lie a distance A from the origin. And when I draw the vector that connects my charge, my piece of charge DQ, to the point that I'm evaluating, my field point, this is now a vector R, and that vector is going to have a magnitude equal to the square root of a squared plus z squared. Okay, so in the potential calculation, the r that appeared in the denominator is a scalar value. Potential is a scalar, it's not a vector. So I take the magnitude of this vector and I find that this is equal to the square root of a squared plus z squared. Okay? And then I'm going to pull the constant out of the integral. Then my calculation becomes the integral of dq over r, and this becomes k times the integral of dq over the square root of a squared plus z squared. Okay? But a squared plus z squared, these are both constants, so this can also come out of the integral. So then this is going to be k over the square root a squared plus z squared times the integral of dq. Now, we've already done this particular integral with the electric field, so I'm not going to repeat that calculation, but you can do it one of two ways. If this is a uniform charge distribution, where lambda is constant, and that's what we're assuming here, okay? If lambda is constant, then your dq integrated around the ring, and actually, in fact, it doesn't even matter if lambda is constant, okay? Because when you integrate around the ring, you're just going to get the total charge of the ring, no matter what lambda looks like. But in any case, you can just directly say the total integral of my charge around the ring is just adding up all of the charge to the total charge, capital Q. So this just becomes capital Q. Or you can look at the functionality of how dq translates into ds, integrate around the ring angularly, and then transform back into your total charge. We've done that before, so we won't go over that here. But this is the end result, and the integral of dq just goes to q. And there's our result. Now notice, I don't have any vector notation here because potential is a scalar. This is why we often like to calculate potential instead of the electric field. It's a scalar calculation. It's often easier to do. You don't have to worry about components. You don't have to worry about symmetry and cancellations and things. You just straight crank through the integral. Okay, but here's the kicker. Okay, remember when we said that potential was the or was related to the electric field, in that the gradient, or the way the slope of the potential changes, is the electric field. Okay, and so mathematically what that means is E is equal to the negative derivative of potential, but this is only for one dimension, okay? And precisely what the actual expression is in its full glory looks like this. Okay, so this symbol, right, and this is how we recover the vector nature out of this, okay? So E is equal to the negative gradient operator on the potential. So what is this gradient operator? So the gradient operator says, take the derivative of the potential in the x direction and attach the x direction unit vector to that value, and then do the same thing for the y and z directions. And then you have your negative sign out front. Okay, so the gradient operator just says take your derivative in each direction, attach your unit vectors according to the direction you're taking your derivative in, and then add that up vectorially and attach your minus sign. So these are individual components, okay? This is the component of the electric field in the x direction. This is the component of the electric field in the y direction. This is the component of the electric field in the z direction, okay? So now we have a way to recover the electric field via this equation. So let's see how this works with our result from this example. So we've found that our result for V looks like this, okay? So this is our result for the potential. Now, this is a function of z, which makes sense because we're along the z-axis, so anything that's going on in the xy directions shouldn't matter if this is a truly uniform distribution. So this function gets smaller as I move along the x-axis, which should make sense. As I move away from my charge distribution, my potential gets smaller. The way we define potential, and the way we define potential is that it is 0 at infinity. So the further away I get from my charges, the smaller my potential is. And so this is a decreasing function this way. Okay, this is a decreasing function this way. But the electric field is equal to the negative gradient of the potential. Okay, it's equal to the negative gradient of the potential. So as your potential increases, your electric field is going to be pointing in the opposite direction. Okay, so I'm getting smaller this way, which means my positive slope would be pointing down. Okay, the change in my potential is going to be pointing down, and therefore my electric field points up if this is a positive charge distribution, right? So that's what the negative gradient implies as far as the directions go. Now, how do we actually calculate it? So in this case, this function, whoops, our potential function is only a function of the z variable, right? This is the only direction variable that appears. So this is the only component that I have to calculate. So this is going to be negative dv dz in the k-hat direction. Okay? Negative dv dz in the k-hat direction. And what is this going to turn into? Well, dv dz from this is the same thing as taking the z derivative of a function that looks like this. Okay? And I like to write my functions out like this, just because it's easy for me to keep track of what's happening with my powers and things like that. Now, k and q aren't affected by the derivative operation, but the derivative of this becomes minus 1/2 to the negative 3/2 times 2z. Okay? And my 2 and my negative 1/2 cancel out. And so this negative sign still is out here. Okay? So another way of writing this is kqz over a squared plus 3 squared to the 3/2. Okay? So this result is the same thing as negative kqz over the square root, over a squared plus z squared to the 3/2. Okay? Now the electric field is the negative of this. Okay? The electric field is the negative of this because E is equal to the negative gradient of V this negative sign will cancel out with this negative sign. And so E is going to be this quantity in the Z direction, or k hat direction. Okay? And this is exactly the formula that we found when calculating the electric field with the integral method. Now, the integral method for a charged ring is not difficult in either the electric field or the potential case. But when you have more exotic charge distributions, like even a uniformly charged disk, if this were a CD or a record and we had smattered charge uniformly over its surface, even then the differences between the potential integral calculation to get here versus the integral you have to do with the electric field is quite stark. And so we already see the differences in how the integrals go. And so it's often easier to do two calculations, do an easy integral and then a derivative instead of a really difficult integral. And so that's why this process is often used to actually calculate the electric field. We don't always do the electric field integral start to finish. Oftentimes we will try to find the potential and then take the derivative and then recover the electric field from that derivative. Okay? But this is an example of how to do it for a continuous charge distribution.